Uh, hey guys, all right, welcome to another lecture on 3D computer vision. So we have a little guest lecture at the beginning, or more of an extended announcement, I would say, but we have Rick Hudson joining us today. So I'm going to hand it over to Rick in just 1 minute. So Rick is industry partner for the class, and honestly just a big proponent of some of the work we do. I met Rick before I even started teaching at UNCC, like way back in 2017 when I first moved to Charlotte. And Rick has just been the nicest person, and really, has made some great connections. Rick actually introduced me to a gentleman named Phil Morris, who actually I work for now. So Rick has made a lot of really great connections, and he's always kind of, involved in the community and looking for projects and kind of helping students move along in their studies, which is awesome. So Rick's a great person to be in contact with, and he has been generous enough to join us today, and he's going to kind of walk through a few different projects that he has in progress, or he's looking for students to work on. So if you're looking for research to be involved with, or less formal projects to work on, then Rick is your man. He's got a bunch of really interesting connections. So I'll hand it over to Rick. Thanks for joining us today. And yeah, thanks, Rick.
Well, thank you for that introduction. It's been a pleasure working with you and with the classes in this semester and in the past semester, and would love to see how we can collaborate and go forward. But thank you, and good afternoon, class. Hope all is well with you and yours. And let me do some screen sharing here. Bear with me. I had everything set up and it just went away. Bringing up. Let's see, can you see anything?
Not yet. Let's see here.
Okay.
No problem. I'm glad we did a test. It gives us more confidence. I'm sure it will work. There we go. Now it's loading. Yep. And let's see here. Yep. So I see a notepad right now.
Okay. What about right now?
Still notepad. It might be locked on that notepad app, maybe.
Let me try this.
All right.
Technology always does us good things.
Yeah, it knows more people are watching. There we go. Now we got your slide.
Okay, thank you. Well, what you see is a list of project topic ideas that are either activities ongoing or things that I would like to and collaborators would like to pursue in the future. And I'll go through them briefly and speak about some various topics and parts. The first you'll see is one called Cotton Boll Identification, Location, and Inspection. And this one is pretty interesting, and it involves, a cotton boll is the wad of cotton that grows on a plant in the field. And if you've ever seen cotton harvested, you know that a large machine that costs a lot of money, and that's a factor, goes through the field and harvests the cotton. And after the harvesting process is completed, if you would look at a cotton field, you'd wonder if anything was done because there's still a lot of white stuff out there. And the reason for that is the machines are set to pick the cotton at a certain level on the plant because the cotton bolls mature at a different rate. And so what you have to do is kind of assess and do your harvesting when you'll get the most, knowing that you'll waste a lot of cotton. And so there are issues that go into that, and the cost of the machine will determine the size of the field and so forth. So there's a lot of waste in the inability to get all of the cotton or to do several passes, since when you harvest, it destroys the plant. So in the old days, when it was picked by hand, there would be several passes through a field harvesting at different times when the plant, the fibers matured. And so there is a potential great role for robotics to play in this part of agriculture, which involves using imagery to locate the cotton on the plant, assess maturity, and direct an arm or some kind of robotic apparatus to pick it. And so, and to do so with an autonomous platform. So imagine a swarm of small ground-based robots or ground-based drones maneuvering through a field, identifying and picking cotton. So it involves a lot of imagery, a lot of analytics, a lot of edge level imagery analytics, and there's a significant amount of work underway in this. And I have some papers I'll be happy to share, but I've had some discussions with some autonomous vehicle and analysis and assessment companies that are interested. People like Cotton Incorporated in North Carolina and globally are interested. So there's a lot of interest in this. So that's one item. Another one is cotton seed inspection and grading. When cotton is harvested, seeds are also harvested. And so there is a desire for some ability in the field to assess the state of the seed and to grade the seed. And they do this visually, they do it with imagery, they do it with measurement. And this is a particularly, this is independent of the first one I mentioned, because this is an immediate need right now as well. And one of the needs, one of the platforms that people are looking at that would have interest in is, think of a mobile device where you could take a photograph of one or more or a group of seed and then assess and generate measurements of the seed and a grading of the seed based on the image. So there's a lot of interest in this. So those are the two kind of agriculture related things that are of high interest. Another one is roof inspection. I know in the past, several class teams have worked with a company in Charlotte that did like building cleaning with drones. And this is a similar thing in that looking at airborne drones, in this case, to image a roof of a building and then assess damage, typically from weather events such as hail. If you own a home or know someone who's owned a home, you know that typically it's liable to roof damage from weather events, and typically people will circulate around and say your roof is damaged and here's how and so forth. And insurance companies will want ways to assess roof damage and so forth, because the roof is probably one of the more vulnerable portions of a home because it's exposed to weather. And so if there were a means to, a lot of the assessment is very subjective. So if an automated means could be developed to objectively assess based on looking at a ton of imagery data, of tag data that identifies various levels of damage and so forth, and develops employs machine learning to develop a means to say overfly a roof with a drone and take imagery and generate on the spot a damage assessment, that would be something of value to the housing industry, to the insurance industry, to homeowners, to business owners, and to the people who go and repair these things. The next one is deals with persons in restaurants. Now, you know, there are a couple of projects on campus that are looking at imagery to identify and assess the behavior of persons, say in crowds and so forth, and determine, say, if there's a threat level associated with that. This is very similar to that, but looking at the specific environment of a restaurant in the current day. So imagine an imagery system that is looking at the serving floor or the preparation area of a restaurant and looking at the motions of people in that space. When are tables being used? Is social distancing being followed? Once a customer or a party is seated at a table, is the wait staff attentive? Has the wait staff gone to visit that? Has there been a period of time when wait staff should have visited and didn't? What is activity like around the cash registers? Are there people standing there and they're not getting attended to, or even getting into a lower level of behavior? Can you tell by the motions or actions of patrons at a table that they might need wait staff to visit? So it impacts efficient use of employees. It impacts customer service. It impacts safety and efficient utilization of restaurant space and things like that. And using real-time edge-level imagery to do that. So this would involve taking a lot of data generated on the space and assessing the behavior of customers as well as employees. The next one is one that's ongoing right now. There's a team working on it. This is a carryover from a prior semester, and has potential to go forward. And that is developing a method to use hand signals to control an airborne drone. The team's working on it right now on some identified motions to put some control signals into the drone based on hand signals. And they've advanced to the point to where they're looking at hardware that would be integrated onto a drone platform, and we have a drone platform. So the reason this one's still up there is, there's always room to carry this further and to build on what prior teams have done and get into more sophisticated motions and controls and things like that. So this will probably be an ongoing project for some time to come. So if you're interested in this kind of things, this is work that you can take and kind of go forward with. And we want to see additional activity in this project in the spring semester and ongoing. And like I say, we're almost to the point of mating to a platform and doing some testing there. The next one involves navigation in a non-GPS environment, and in this case, underwater. You can't get a GPS signal underwater. So if you want to navigate underwater or have a vehicle or an AUV that acts underwater, they say to follow a specific path or to record where it's been, you can't depend on GPS. So there are two parts to this. One, mating an inertial measurement unit to sufficient processing to be of use, and potentially employing imagery that if you go over an area and you collect imagery of that area and you know you're going to be going over this with a vehicle that needs this navigation capability, how can you use that imagery to in conjunction with the IMU to help you know where you are and how far you've gone and how you get back to a starting place. A similar underwater application is marine imagery. We'd like to stand up a team that would look at a large body of images of marine life and develop a method, develop a capability for automated identification of that marine life. This is a grouper, this is a basking shark, this is a white-tip shark, this is a reef shark, this is a lionfish kind of thing. There's particular interest in this as far as identification of marine life, counting the incidence of marine life in a given area. And I think, given that there are some variations in marine life, some follow-on over the horizon kind of work could be done in this, in even identifying a particular individual within a species based on unique markings on the body, like people do now. A next one is use of NC LiDAR data and imagery to identify sites of potential archaeological interest. The state of North Carolina has amassed a significant amount of LiDAR data, particularly in the eastern part of the state, of sub-meter resolution. And they did so for use in flood control and hazard management of issues in the coastal plain as storms come in. This part of the state's been occupied for really thousands of years by Native Americans and then early colonists following that. You might be familiar with the story of the lost colony, which is still an active archaeological pursuit. This LiDAR data, we think, may be useful, particularly in conjunction with imagery of airborne and satellite sources, to identify sites of particular interest for archaeology. Has there been human habitation there over a long period of time? One area of interest is copper mining. Early Native Americans saw value in copper as a metal, and so they would dig copper pits to extract copper for use. And so hallmarks such as that may be something, as well as old stream beds, old ford locations where people would cross streams on foot before there were bridges, old trails, old villages, habitations, things like that, that may be as yet undiscovered, could be extracted from this data that was collected for flood management and hazard control. And the last one is not really a direct imagery analysis, but the drone I mentioned that we have is the ground link system is called a HereLink system, and I think that's the company that created it. And so interested in pursuing mating augmented reality to that. There are a couple of companies out there that do this for the DJI systems, but doesn't exist for this. And so I kind of tucked that on the end for anyone who might be particularly interested in Android type applications and taking visual imagery and deploying and depicting it in an AR type of platform. So Stephen, I'll turn that back over to you for anything, any questions.
Great. Well, thank you, Rick. Awesome. So yeah, if you have any questions for Rick, please throw them in the chat window. And then I have one question, Rick. So if students are interested in getting involved in any of these projects, how can they get in touch with you?
Well, my email address, and I apologize, I should have put that up there.
No problem.
Is rhudson@uncc.edu. And Dr. Welch, feel free to share that with anyone who might be interested.
Yep, no problem. We will do that. We'll take care of that. Absolutely. And yeah, thank you for your time. And guys, just in general, there's a bunch of ways to get involved at UNCC and other places. But in projects like this, and this is something that I did as an undergraduate, I was involved in a few different research projects, and it's a really great way to improve your engineering skills, but also make some connections that could turn into jobs or could turn into all different kinds of things. So if one or more of these sound interesting to you, then yeah, please reach out to Rick, and he can tell you more.
Certainly. Well, thank you. And on the outlook on the connection, well, I want to note there's a senior project that we're working on this semester between engineering and computer science. And one of the things we hope to do for it in the spring is to get some of the film and communications folks here to do a video log of that. So
cool.
One thing I'd like to do is turn that into a video resume for some of the students.
That'd be great, right? Yeah, imagine that on your LinkedIn, right? That's a nice thing to have on your LinkedIn as you're looking for jobs and stuff. That's awesome.
So we would, if we do any of these projects, we'd want to do the same thing. I don't know if we'd be able to, but that's one of the objectives.
Yep, great, awesome. Well, great. Well, thank you so much, Rick. We really appreciate it. Feel free to stick around. We're going to hop into lecture now, but if no need to stick around if you don't want to, obviously. But feel free to stick around if you'd like to. Anything else before we wrap up?
No, I really thank you for this opportunity, and looking forward to chatting with any students who might be interested in any of these projects in any capacity.
Great. Well, thanks again, Rick. We really appreciate it.
Thank you.
All right, great. Okay, guys, Arvind and Rohan, anything before I hop into our regular lecture here?
One thing is, could we have the slide from Rick so that we could keep the slide on Canvas so that students can actually look at it when they have free time?
That'd be great. Yeah, Rick, if you're still on, would you mind emailing that slide to either myself or Arvind or Rohan, and we can put it on Canvas so students can review it?
I will do that right now. Thank you.
Great. Awesome. Thank you. All right. Anything else, Arvind or Rohan? Any other announcements?
Nothing from my side, Professor.
Nothing from my side as well, Professor.
All right. Well, let's get into lecture. Great. All right. Well, thanks for joining us today, guys. We have some more 3D world stuff to talk about, so let's get into it. I look kind of rough today. I got to shave. Man, when you don't go anywhere, you just, why shave, right? All right. So let's do this. Let's make the screen share the main focus, not my video. Okay. All right, so we have been talking about some cool stuff that is related to some of the things that Rick has been just mentioning, especially the 3D underwater mapping. We've been talking about 3D computer vision. How do you take 2D images and turn them into 3D maps, things like that. And last time I shared with you this animation that I made at my last job where I took a bunch of images and I used our IMU actually in our car to project those images into worlds. Well, I used some math that we learned and the IMU data to make this map basically. And just to review, we started with this what's called a pinhole camera, a model of the camera. That led us to do some kind of similar triangle math that led us to these equations. We kind of made our equations a bit better by adding a few things. We put them in this thing we call the intrinsic matrix that describes, these are 4 parameters that describe how your camera works. And then, let's see, what did we do then? So I asked you some questions. Oh yeah, and I asked you a trick question. So I asked you this question. So remember I said, okay, here is the intrinsic matrix for a camera, right? Here it is. Given a point in image space with coordinates 200, 100, it's at some point in image space, I said, please tell me the point in world space where this pixel would correspond to, right? So where is the point in world space that matches this point in image space? And what was wrong with my question? Sometimes I try to trick you, not always, but I did try to trick you here. Why is my question impossible? What's the problem here? Throw it in the chat window. Yeah, so there's an infinite number of answers. Yep, totally. So yeah, thank you, Pooja. Yep, thanks. So yeah, there's a bunch of answers, right? But not just any answers, right? So all the answers lie along a certain ray, right? They lie on a certain ray. But it could be any point along this ray, because any point along this ray of light will land on the same point on your image sensor. And another way to say this is that cameras don't measure depth. They don't measure distance, right? They really just capture the light that hits the photoreceptors. Okay, so, and then I asked you, I said, okay, you know, if that's really true, then how did I make this map? You know, how did I do this? If the equation is impossible to solve, how did I find these world points that I'm scattering? Does anyone know? What did we say last time? There's a bunch of ways to do it, but I did one of the simpler ways. What assumption did I make to make this map that allowed me to solve that equation? The world is flat. Yep, I assume the world is flat. Not in like the flat Earth sense. I didn't assume that the world's not a globe. I just assumed that the local region around my camera is flat. And when you do that, you can constrain one of these variables. You can basically set the value for W. And if you set the value for W, you can solve the equation. So that's the idea. Now let's keep rolling here. So what I'd like to do now is I would like to get into talking about why are we using an intrinsic matrix in the first place. So, you know, we have these four variables, our phi x, phi y, delta x, delta y. Why did I have you put them in a matrix? Why did I want you to put them in a matrix? And the answer really is that if we put them in a matrix, we can turn our problem, our math problem, we can turn it into a matrix equation that is actually a lot easier to work with and easier to optimize. But the way we do it is a little bit funny. So this is the kind of equation that we're going to be using in this module. We're gonna add to it a little bit, but this is kind of the spirit of the equation. So here's our intrinsic matrix right here. And notice that I've added this column of zeros. Don't worry about that too much right now. We'll talk about that in a little bit. But what I really want you to pay attention to is so you should be familiar with U, V, and W. What were U, V, and W last time? Tell me again. What are U, V, and W? What do they represent? Yeah, it's the world coordinates, right? It's the location of the point in world space. Remember, we said the origin is going to be the center of our camera, and then this is the location of the point in world space relative to that origin. Okay, and what are x, y again? What are x and y? Yeah, image coordinates, great. Okay, perfect. Now, notice what I've done here, right? So yeah, I have this UVW vector, and I have this XY vector. What have I done that's kind of weird here, right? Look what I've done. So I put these ones on the end. That might seem kind of weird, like why did I do that? So I put these ones on the end, right? And I've also introduced a new variable. Does anyone see the new variable? Where's the new variable that I introduced without saying anything about it yet? Where's the new variable here? Thank you, Sean. It's lambda. So this is the new variable lambda, right? Okay, cool. So why am I doing all this? Why am I doing all this crap? So it turns out, so remember that the equations we started with these fractional equations. It's a little bit small, but right here, remember we started with like u times phi over w plus delta x. We started with these equations. And I'm proposing that we change to these equations because it's going to be easier to solve these problems with computers. And if we change these equations, right, or like, you know, why would we want to change them, right? And it turns out that these equations, the way they're written, and remember we derived these equations, I'm going to make it a little bigger. We derived these equations from similar triangles. But an equation like this here, it's kind of not fun to solve with an optimizer, with a computer, because we're dividing by W. So dividing by this variable W, it makes the equation nonlinear because we're dividing, we're not just adding and multiplying. Makes the equation nonlinear, it makes it harder to work with. So it turns out that we can represent the same system of equations, we can represent it using this matrix multiplication problem, But to do that, we have to introduce a trick. And the trick is it's what's causing this 1 to appear here. It's this idea of homogeneous coordinates. Homogeneous coordinates. You'll hear that a few times in this module. So the idea of homogeneous coordinates, it's pretty simple. The idea is we add an extra degree of freedom to our variables. So this is a plot from Prince's computer vision book, and he's trying to explain the idea of homogeneous coordinates. And the idea is that when we express our point in homogeneous coordinates, the idea is that every point on an array is going to have an equivalent representation in homogeneous coordinates. And we won't spend a ton of time on that idea. Don't worry about that too much. The main thing I want you to pay attention to is just how are we going to convert to and from homogeneous coordinates. So here's an example for you. So if I have the vector 1, 2, let me make this a little bit bigger. If I have the vector 1, 2, and I want to convert to homogeneous coordinates, all I do is I tack on a 1 on the end. So I just tack on a 1. So I just add an extra variable to my vector, and it's always going to be a 1. If you want to convert from homogeneous back to Cartesian, which Cartesian coordinates are what we're using by default in this course, if you want to go from homogeneous to Cartesian, then what you do is you take a vector like this, and you divide the whole vector by the last value. So I have 3, 6, 3. I divide the whole thing by 3. And then that result, I take that result and I just lose the last value. So 3, 6, 3 becomes 1, 2. So there's more about this in your reading. So have a look at it. You know, normally I'd like to spend a little more time on this, but this is definitely something I would quiz you on. So make sure you're comfortable going from Cartesian to homogeneous and homogeneous to Cartesian. So that's the idea of homogeneous coordinates, and it's just a different way to represent our points by adding an extra dimension. It's gonna linearize our equations, so it's easier to do the optimization problems we need to solve some of these problems we're gonna bump into. So those are homogeneous coordinates. They're not too crazy. Prince, in his book, he's trying to kind of capture the idea that homogeneous coordinates capture the idea of any point being along an array. And this kind of makes sense to me, but honestly, I think there's a really cool interpretation of homogeneous coordinates, like a cool visual interpretation, but I haven't seen anyone do anything on it. I wish like 3 Blue 1 Brown would make a video about it or something, because I think I would really enjoy that. But so I think that, yeah, I think there's some cool way to look at it, but I'm not exactly sure how to visualize it. It's something I've been thinking about. Let me know if you figure it out. But all you have to know for this class is that homogeneous coordinates, basically we're adding an extra value to our vectors. And if you go from Cartesian to homogeneous, you add a 1 to the end. And if you're going from homogeneous to Cartesian, divide by the last number in the vector, and then lose that last value. So that's the idea. That's homogeneous coordinates in a nutshell. And the reason we do it again is because this equation, if you work this out, and if we had a whiteboard, I normally would, but we need to move a little bit faster today because I want to get to the next lecture. But if you work this out, it turns out that this equation is identical to these equations, except there's an extra variable in here. And we'll talk about that a little bit more in a minute. But you have to have an extra degree of freedom to support these ones that we're adding. But by doing this, you make the whole system linear, so it's easier to work with. So we're just doing some mathematical shuffling, really. Okay. So let's see here. Yeah, I wouldn't mind us walking through one of these examples. We don't have a ton of time, unfortunately. Let's see here. How do we want to spend our time? So we definitely need to hop into our image interest point detection lecture. I'll tell you what. Let's do this. So here's my last question I have for you in this lecture. And let me let's talk through this question a little bit. So yeah, normally I'd kind of leave this as an open question for the class, but let's just talk through it directly instead of taking the time to have you guys answer it yourself. Normally I would like to do that, but because we're a little short on time today, we'll go ahead and talk through how it works a little bit. And did I copy this one? Yeah, I did. Cool. Okay, great. All right, so here's a question. And I would like us to solve this using the matrix equation this time. Last time we used the similar triangle equation. So I would like us to solve this problem using the matrix equation. So let's walk through it here. So I've given you a point in world space again here. Here's a point in world space, right? And I'm asking you to find the corresponding point in image space. And it's really straightforward. So, but I just want to show you how this lambda thing works and why it's not a big deal. So let me go ahead and start working through this equation. So I'm going to write down my equation here. So lambda times xy1. So we are solving for x and y. Lambda times xy1 is equal to, and I'll pop in my intrinsic matrix here. We have the intrinsic matrix is equal to 1,000, 0, 960, and then let's see, 0, 0, 0, like that. And then 0, let's see, it's 1,000, 1,000, 540. Cool. When COVID is over, I'm going to be excited to use a whiteboard. It's going to be awesome. All right, so this goes like this. There we go. Okay, cool. So that is the intrinsic matrix. I've added this column of zeros we need to make the dimensions work. And now I'm going to add in my UVW. So we have UV and W here. So we've got 1,000 like this, 1,000. I've got negative 2,000. Cool, I've got 10,000. All right, and I've got 1. So, and for the record, you know, what I've done is I've just converted this vector is in Cartesian coordinates, and I've just converted it to homogeneous. So this is now in homogeneous coordinates. Okay, so next we are going to do, I think we'll just go ahead and do our matrix product. That shouldn't be too bad. So we've got a 3 by 4, a 3 by 4 matrix, and I've got a 4 by 1. So our result should end up being 3 by 1, which should match this dimension. So let's try it. So we'll go row by column. So this first row, I've got 1,000 times 1,000, which is 1,000,000. And I've got 0 times negative 2,000, which is 0. And I've got 10,000 times 960. I was going to do this in my head, but maybe not. Let me get a placeholder here. So here's going to be our result. So I've got 1,000,000. Actually, yeah, we can kind of do that. So I've got 1,000,000 plus, so 1,000 times 1,000 plus 960 times 10,000. So let's try that. So I'm gonna just have my calculator here. Let's see. So 1,000,000 plus 10,000 times 960. So I get 9.7 followed by a bunch of zeros. I might convert this to scientific notation. So I think I get 9.7 times 10 to the, I believe it's 6. I think this is 9.7 million. If you don't mind, someone please check my math here. This is what I get. I get 9.7 times 10 to the 6th. Okay, so I'm going to keep moving here. And yeah, if someone can check my math and let me know if they get the same thing. So here I have 1,000 times negative 2,000 for this row times this column. So 1,000 times negative 2,000 plus 10,000 times 540. Okay, so I think I get 3.4 million, I believe. So I think I get 3.4 times 10 to the 6th for this value. Okay, and then for this last one, I have 0, 0, 1, 0. This one's going to be easy. 0, so 0 times this, 0 times this, 1 times this, and then 0 times this. Let me just ask the class to make sure you're with me. What goes in this last spot? What number should I put here? Thank you, Ashish. So yeah, it's 10,000. It's 10 to the 4th, or 1 times 10 to the 4th. Okay, cool. Alrighty. So this equals this, and I'll just bring this down. Okay. So let me ask you now, do we have a solvable system? What would you propose as a next step? How would I solve for x and y? I'm getting close, right? Any ideas? Ideas on how to solve for x and y? How can we solve this system from here? So Abhijit says choose a lambda. Oh, we could, yeah, it's an option. We don't have to work quite that hard though. Let me propose something. So keep thinking, guys. Yeah, so Ashish, you're on the right track here for sure. So, and I think Ashish is kind of taking a step ahead, which is great. I think I know how Ashish got there. So let me show you what I recommend. I would throw this lambda in here just to help me think. So I'd put this lambda, so it's a scalar times a vector, so the scalar gets multiplied by everything in the vector. So this is lambda x, lambda y, lambda is equal to this whole thing, 9.7 times 10 to the 6th, 3.4 times 10 to the 6th, and 1 times 10 to the 4th. I'm just going to put 10 to the 4th. Okay. So yeah, so the idea now is we actually know lambda right away. And we don't have to work too hard, right? So lambda just turns out to be, you know, this has to equal this, so lambda is just 10 to the fourth, right? There it is. So if you want to find out what x is, you just divide both sides of this equation by lambda. So x should equal 9.7 times 10 to the 6th divided by 10 to the 4th, which I believe is 9.7 times 10 to the 2nd, also known as, I believe it's 970. So this is what I get for x by realizing that lambda is 10 to the 4th. So 10 to the 4th times x equals 9.7 times 10 to the 6th. Solve that equation, you'll get 970. So this is the idea. This is definitely something I could ask you on a quiz. And hopefully that's not too scary. And it's the same thing you would get by using those equations we developed from similar triangles. But this is a little more elegant way to solve it that's more useful computationally when we're solving these problems on computers. If you have any questions about that, please throw them in the chat window. Otherwise, I'll keep moving here. I hope that all makes sense. So let me hop back here. Okay. All right, so we use this equation. I hope that makes sense how it works. Okay. So there's one thing left. There's one thing left that we have to address if we're going to get to a plot like this. So to make a plot like this, right, I have to have an origin, right? There has to be an origin somewhere that all of the points are relative to. And just so you know, actually, I made this plot using matplotlib scatterplot. Like there's nothing that fancy about it. I take all the pixels in the image, I project the ones that I can to the flat world, and then I just scatter a bunch of points using matplotlib scatterplot. It's actually a funny story with this plot. This takes a long time to render because matplotlib is slow for lots and lots of points. And I had to give a presentation in California. So I remember this specifically. I had to go to the airport at like 2 o'clock. And I started rendering this and I was like, crap, I can't render the video. This is actually a video from a bunch of matplotlib plots. So I started the script when I was in Charlotte, and then I got on a plane and I had the script staging the images to Dropbox. And then when I got to California and I landed, I pulled them down from Dropbox and then I rendered out the video, and then I used it in the presentation. So it was last minute, but it was a good thing to have in the presentation. So, but anyway, it's just a matplotlib scatterplot. That's all there is to it. Yeah, it was awesome. I feel like my career is sometimes not awesome and super lame, but that was one of the cool moments. I felt cool that day. That was one of the 2 days a year I felt cool. Okay, so it's just a scatter plot, and there has to be an origin, right? There's got to be an origin. And my point that I'm making here is that all of the equations that I've shown you so far, where's the world coordinate origin for all the equations I've shown you so far? Where's the world coordinate origin? Where did we define the origin of our coordinate system to be in our pinhole camera model? Does anyone remember? Where did we say that the origin has to be? In this picture, right? Where does this origin? You know, this is the camera right here, right? Yeah, it's the close to the principal point. It's the optical center here. Remember, this is like it's inside the camera, right? So we said the origin is fixed inside the camera, looking straight down the barrel of the camera or the lens of the camera. The problem with that is that if you assume, so you know, all of our right triangle math, it only works if the origin is here. But in practice, your camera can be moving, right? And if your camera is moving, then your math needs to extend to cover different viewpoints and different translations of your camera. So that's the last. So we get the parameters actually of the camera, right? The image sense 3D space. And the idea we'll use here, it's pretty straightforward. It looks a little scary in math, but it's really not bad, I promise. So you can take a point in world space and you can map it to a new point using this kind of operation. So what you're looking at here is if I have a certain point UVW and I want to move it around in three-dimensional space, I can do that using this is called a rotation matrix, and this is a translation vector. The translation vector is a little easier to understand, right? The idea is, you know, if I want to move 100 millimeters upward, up is the V direction, and actually, it's up is a bad example. Let's say if I want to move 100 millimeters to the right. The right is the U direction, so I would add a 100 millimeters right here, and I would shift my point 100 meters to the right, or 100 millimeters to the right. The translation part is kind of simple. The rotation part's a little more complicated, but I wouldn't sweat it too much. This is just a matrix that when I multiply by it, it will rotate my viewpoint basically. So that's the idea, and this is how we express it mathematically. This is not something I'd quiz you on directly. This is maybe a little bit, but nothing too hard. But this takes a viewpoint in 3D space and it moves it, right? And we have to model that movement if we're going to make a map. We have to model how the camera moves. So that's the idea of this equation. Here it is written out as a full matrix. Here's kind of a compressed version. You can call this matrix omega. We call this vector tau, and if you put them together, you get an equation like this. And now what we really do, the reason I'm bringing this up is because really I want to get us to what is like the core equation in this unit. Sorry, hold on. There it is. This is like the equation. So this is the equation I'd like you to be comfortable with for your quiz. I might give you a little bit of extrinsic stuff, but mostly it's going to be intrinsic. But this puts everything together, and this is in the reading as well. This puts the whole world together. What we have here is some world coordinates in homogeneous coordinates. This is the extrinsics. So if I have like a world coordinate defined from a different origin, so if I said, like if I was trying to do this map in reverse and I said, hey, you know, where will this pixel on the map or this point on the map, where will that be in the image if the camera is here, right? So if this point is defined relative to an origin over here in the bottom left corner of the plot, for example, and I want to know where that point in world space is going to show up in my camera, then I have to know the relative rotation and translation goes from world coordinates to image coordinates to adopt to go to homogeneous coordinates. But this is the whole thing. So I hope this isn't too scary. It's really not too bad. The reading does a nice job too of explaining it. We're going a little faster here than I'd like to in general, but we got to make sure we have time for a couple other topics in this module. So this is the idea. If you have questions, please post on Piazza. As usual, you know, the main thing if you're studying is to review the questions that I've asked you in class and do the reading. So this is the equation though. There's a ton of problems in 3D computer vision, and most of them involve some permutation of solving different parts of this equation. That's really the idea. Just to give you a sense for what kind of problems you can solve using this equation, the first problem is what's called intrinsic calibration. So intrinsic calibration, that's the problem of estimating this matrix. This is very important in areas like robotics. So if I want to have a robotic arm, you know, pick up an object or something, right? I have to estimate this for my camera. Otherwise, this basically lets me know, you know, if I want to pick up an object that's like 10 millimeters to the right and 5 millimeters down, I have to know, you know, how to map from what I'm seeing in the image from the camera to world space. And having this matrix is really important. So I think we have a lecture on this. We'll talk about it if we have time, but there's a process you can use to calibrate your camera using checkerboards that can solve and figure out what these parameters are. Extrinsic calibration, this is figuring out where the camera is relative to the world. I'll get into this in a minute, but to make this map, I had to know where the camera was mounted on our car, like for example, how far above the road surface the camera was mounted. That would be extrinsic calibration. That's where we're estimating, in that case, we're estimating tau, these displacement vectors. The problem of inverse projective mapping, this is if we're trying to figure out kind of a map of the world. We're trying to find W in general. There's this really cool problem called bundle adjustment. Bundle adjustment really, if we look at maps, like remember I showed you this, this map at the beginning, right here, yeah. So making a 3D map like this, this is solved using a problem called using an approach called bundle adjustment, which is what you'll be using in your programming challenge. You're not going to write any bundle adjustment, don't worry, you're just going to use a library. But a bundle adjustment algorithm, it actually simultaneously solves for all four of these values, all four of these values, all together to optimize some global objective function. And then finally, visual odometry. This is a cool idea. This is using a camera alone to estimate how a camera or a car or a robot has moved through space. So here the idea is if we can estimate omega and tau, given world coordinates and image coordinates, we can know the path that something took through space. So this is used in robotics. So there's a bunch of different cool concepts in here that all kind of center around this equation. Okay, so I think I'm just going to briefly touch on this because we don't have too much time left. But if you're curious about the math or the code that I use, rather, I've shown you the math. Now here's the code. In this last part of the notebook, I walk through the code that we need to use to actually do this mapping. Like here, for example, I'm setting up that tau vector. So like this 1549, this is 1549 millimeters. It's like 1.5 meters. This is exactly how high above the ground the camera on our car is. So here I'm setting up some of the calibration stuff. Here's the intrinsic matrix for the camera that we use on the car. Here's our equation. Again, I'm doing some simplification to it. Here's where I plug in that assumption that the world is flat. Let's see here. And then I have to solve this matrix equation, and then I use that solved matrix equation to project my points into world space, and I end up with kind of a nice projection where I'm just taking pixel values and I'm putting them into world space. So that's the idea. I wish I didn't have to gloss through some of the code, but if you're curious, please have a look at it. I won't quiz you on this code or anything, so the quiz would only cover the questions we covered in class. Okay, so that's all I have to say about the Pinhole camera model. I hope that all makes sense. Please throw any questions you have in the chat window, but if there aren't any, I'll hop into interest point detection, which is another really big important piece of doing 3D computer vision. It's a little bit different, but it's an important piece. Okay, so we've had a 5-second break. Now we're going to hop into interest point detection, and this is a huge area of computer vision. You know, you could spend months covering this area. There's a bunch of history, a bunch of stuff has been tried, but let's get into it. And there's a couple of project groups that I know are using some of these techniques, so they do come up in all kinds of different computer vision problems. So if I go back to here for a second. You know, to make a map like this, you know, I mentioned that for me, when I made this map that I showed you, I used a really fancy sensor to figure out where my car was. I used an IMU. But this map was made actually without an IMU. So this is made using some other techniques. And a big important part of these techniques are using what it's called interest point detection and description. And the idea here is, can I take two different views? Can I take two different views of the same thing? Here's a brick, ball, and cylinder from two different views. And can I match them, right? Can I figure out that, hey, this point matches that point? Because if I can do that, I can start to do some 3D reconstruction, basically. That's the idea. So all I want to talk about in this lecture is how do we find those points and how do we match them? Because it's surprisingly complex, as you may have guessed. So let's get into it. So first of all, let's think about why this problem might be hard. So here's an image, and I've taken some zoomed in patches from 3 different regions of the image, and I'm showing the pixel values, right? But I'm also showing a little plot, a 3D plot of the RGB intensity values. And if you think about it, if you were trying to track a point from image to image, right? If you're trying to track a point in a video, for example, which of these 3 points do you think would be easiest to track? So throw it in the chat window. Would it be this one that's kind of on the white surface? Would it be would it be this point that's on the edge? Or would it be this point on the corner, right? Which one of these 3 do you think would be easiest to follow from image to image if your camera or your subject was moving? What do you think? Corner, white area, or edge? Yeah, corner. So a lot of people say corner. Yeah, totally. So the answer is corner. Let's get into why. So tracking corners is generally a good idea. So let's talk about why for a second. And I guess I don't quite have a slide on why, but the reason is this. So let's imagine that you have 2 images like this, and you're trying to kind of track, you know, from this image to that image, where did this point move, right? The problem with tracking white space is that this point here, it looks just like this point over here, right? They look identical. So it's going to be very hard if you have 2 images to actually know that you found the correct match, right? If you're trying to match the same point in 2 images. This point does a little bit better, but it actually runs into an issue known as the aperture problem. What's the problem with this point, right? Why might this point be difficult to track? Why could this introduce tracking problems? So it's a straight edge, sure. And the challenge is, right, if you moved this box a little bit down, it would look identical, right? So it's going to be very, if you move this box along the edge, it's going to look very, very similar. So it's going to be hard to match to the next image. Now this point is really great because if you translate it and if you move it to the right, to the left, up or down, there's going to be a big shift and you can detect that. It doesn't look just like anything in the neighborhood. It looks distinctive, right? It's a good point to track. So that's the idea here. And one of the first people to think about this problem was this researcher named Hans Moravec. He worked on it was the robot after Shaky. It was the Stanford cart robot. And he developed an algorithm to find corners to track. Now we won't spend too much time on the math here, but this is the equation that he came up with. And it's actually really, really simple. It might look a little bit hard, but it's not too bad. All he does, he takes a little window of an image. This is a windowing function. He just says, give me a little window of an image, and I'm going to take the image, and I'm going to take a copy of the image, and I'm going to slide the copy over the image, and I'm going to take here's the square difference, basically. I'm going to subtract those two. And whichever subtraction, if the subtraction yields a really big value in multiple directions, then that shift must have created a big signal, and that should be a good point to track. That's the idea. If that makes sense, great. If not, don't worry about it too much. But the idea, if you think about this corner, if I took this corner, took a copy of it, slid it around, there'd be a big difference because moving it a little bit is going to make a big difference between pixel intensity values. If I took this flat region, right, and I take it, make a copy, slide it around, there's going to be very little signal. It's going to look the same. There's going to be very little difference. So that was his idea for detecting which points would be good to track. So let's have a closer look at his idea. We won't use exactly his idea because in 1988, these two researchers, Harris and Stevens, they published some improvements to Moravec's corner detector. This is an excerpt from their paper. We won't get into the mathematics too much. But they made a few improvements, and the Harris and Stevens corner detector, it's implemented in OpenCV. So we're gonna have some fun with it now. So I'm gonna import OpenCV. I don't think we've really used OpenCV in this class too much. It's a really nice library. It's a little bit older, but it can do a lot of really nice stuff. And generally, it's going to be faster than a lot of other image libraries. I'm going to open up our image. Here it is. So here's our brick ball cylinder image. I'm going to convert it to grayscale. I'm going to use the OpenCV convert to grayscale method. There's other ways to do it. If you remember way back in the very first module, we converted to grayscale using np.mean, right? And I just want to show you something. So I'm gonna do a little timing analysis using this time it magic function. So I'm gonna time our old method that we used back in part 1, and I'm gonna compare it to how long it takes the OpenCV method. So let's have a little look here. So I'm running a little timing test on my MacBook. Hopefully it won't catch on fire. Okay. So our method from module 1, it took around 12.8 milliseconds per iteration, right? And what do you notice, right? How does OpenCV compare, right? It's pretty dramatic, right? So OpenCV is like, how much faster is that? It's like 40 times faster or something. And the reason it's written in C++ and it's got a bunch of optimizations. So in general, OpenCV is going to be faster for stuff like this. So it's a good thing to know if you're doing real-time computer vision. Great. All right. So let's hop into analyzing this grayscale image. And like I said, we'll use the Harris corner detector on this image. If we run the Harris corner detector, we get an image out of the same shape. And the reason for that is that really this detector that we mentioned, it's really computing a corner score. So this is the result that you get out. And notice that there are some kind of glowing regions where our corner detector has computed some higher values, but it's kind of noisy. It's not great. Excuse me. Let me go ahead and ask the class, what's a good way that we learned about way back in module 1? What is a good way that we might reduce the noise of this corner detector? How can we reduce noise in images like this? Yeah, blur. Yeah, thank you, Sai. Yeah, we can totally do a blur. So I'm going to blur our image using, again, an OpenCV Gaussian blur. Again, we learned how to do this in Python back in, or in NumPy back in module 1, but here I'm just going to use OpenCV. So there's our blurry image, and I'm going to run my corner detector again, and there's a few parameters you can play with. But here you can see now we're getting some nice kind of bright glowing regions on the corners of our brick and kind of on the corners of maybe the corner of our cylinder and ball. And let's do a little threshold. So I'm just going to do a little threshold here to kind of pull out those values. So here are all the regions that had high corner values with that corner detector. So we found corners here. And again, here's the original image. So we picked out that corner, kind of got this corner. Now, there's still some kind of problems here. Like this is, I'm using an algorithm from 1988. I wanted to kind of show you the history a little bit. Does anyone see a problem? Look at these detections with me, right? Does anyone see a potential issue with the corners that we've detected? What could be better? Any ideas? And the idea here is we're trying to find good points to track, right? We're trying to find points in our image that are going to be good for us to see from multiple viewpoints, so we can take those multiple views, solve some 3D equations, and make a 3D reconstruction. That's the idea. What could be better about these points? Linearity, sure. One thing that I noticed, so have a look here. If you notice, it's not just picking up one pixel, right? See how it's kind of picking up a neighborhood of pixels? So that's kind of not great because we'd like to have just one point to focus on. And turning a neighborhood of pixels into one pixel, there's a bunch of ways to do that. And it's kind of known as non-maximum suppression. And this is not something I want us to really code from scratch. It takes a little bit of time. So again, we'll use a published result in a paper called Good Features to Track. This paper came out in 1994. This is by Carlo Tomasi and Jianbo Shi. Carlo Tomasi is actually still a professor at Duke, so not too far away. He's in North Carolina. And this combines some of Moravec's ideas with the Stevens corner detector with a non-maximal suppression. It's been cited a bunch. It's a very popular method. So we're going to use it here. And we're going to use the OpenCV method. It's called Good Features to Track. You get to tell this method how many corners you would like. There's a few parameters you can play with, quality level, things like that. The min distance parameter is really cool. Any guesses on what this does? Any guesses on what the min distance parameter does in this Good Features to Track function? Yeah, it's the minimum distance between 2 points, right? So what this is saying, it's saying it'll never give us 2 points that are closer than 25 pixels, which is pretty useful because you might not want a bunch of points in one location, right? So if I run this, I'm going to get 50 different points. OpenCV has kind of weird dimensionality. They give you a 50 by 1 by 2, which we can deal with, but it's a little bit weird. Here are the corner points. And if I plot them, I get something like this. So there you go. So we have a bunch of, hopefully you can see these little cyan points. So these are the points that this method believes will be good for tracking. And some of them are great. So like these corners, that's a great point to track, right? And there's some of these kind of details on the brick that the algorithm believes will be good tracking features. Now there are exactly, so a few things, right? So so Sai is asking, why does the brick have so many points on it? Yeah, does anyone have an idea? So remember, this is based on Moravec's idea, which is that if I take a little image patch and I take a copy of it and I slide it around, it's going to have a big difference, right? Why does the brick have a stronger signal, right? Any ideas? Does anyone know the answer to Sai's question, right? Why does the brick have so many points? Yeah, it's the texture, right? So I think Nick has said it well, right? So it's got a really rough texture, so that means a lot of contrast. So it really triggers those the Moravec detector when it slides around, right? It's gonna have really high values. In practice, you might not want all your points on the brick, right? And I believe we could just try an experiment right now. So if I made this really big, like 100, I should be able to spread those out. And there's other parameters you can change. This is a little better now, maybe, right? It's detected less points, but they're a bit further apart. And the cylinder is very bland, right? It's hard to get good points on there. So, but with most of these methods, you can tune them and you can play with some other thresholds. There's other things you can do too. There's ways you can maximize the contrast of your picture. There's a method called CLAHE, C-L-A-H-E, that can maximize the contrast of all the regions. So there's stuff you can do, but based on this image, and it's not that big of a deal for us right now, most of the points are on the brick because it has the most texture. It has, in theory, the best points to track. Now, I want to make one more point before we go on, no pun intended. There are approximately 4 points on this image that are actually very bad to track. there are 4 points that have been detected that really are just going to be really confusing for our algorithm. Does anyone know? Does anyone see 4 points that, so the ones in the ball like this is okay. It's not too big of a deal. There's 4 specific points that they're going to move differently than the objects actually move, which sounds kind of funny, but it's true. There's 4 points that aren't actually corners. Yeah, so Nick has said this really well. The points where the brick pixels intersect with the other objects, yes. So if you see this point right here, if the camera moves, which it will, if the camera moves to the side, this point actually is going to, the appearance, because this is not a real point in the world. This point, this corner, it's just a result of how the cylinder is in front of the brick, right? It's not a real corner. This is not a physical point in the world. There is no actual area of contrast in the world right there. It's just how we've captured it. So this point here, this point here, this point here, and this point here, these will not move in the same way as the rest of the scene because they're a result of parallel acts. They're a result of how one object is in front of another. So later we'll get into how to handle that. But these 4 points are not going to be great. And there's no way to know right away if those are bad points. Really, you have to solve that when you get to the 3D part. Okay, so let's get into tracking. How can we track points from image to image? And again, the idea here, right, is, hey, I've got some points, I found them. Now, can I find the same points in another image that's a little bit different? So notice this image, it's the same stuff, but it's from a different viewpoint, right? So can I track these points from image to image? So there's a bunch of ways to do this. One of the simpler ways is to do something called sparse optical flow. Sparse optical flow. One of the most popular methods is called the Lucas-Kanade method. It's built into OpenCV as well. It's named for one of the researchers is Takeo Kanade. He has published, I think, more papers than anyone in computer vision. This guy's published like 300 papers or something crazy. And this method is named for a paper he co-published with Bruce Lucas. So it's a pretty simple method, but again, you'll notice in this lecture, I'm going to kind of gloss over a lot of the math. It's very detailed. There's a bunch of little steps going on. We could spend the whole lecture talking about the math that goes into this. For now, for you being computer vision practitioners, I would like you to know that these methods exist, that they are implemented in OpenCV, that you can use them, that you can tune them, and then if you end up on a problem where you really have to dig deeper, then I'd go read the paper. But here, you understanding the exact details of how these methods work is not too important right here. But at least you know what they are, you know that they exist in OpenCV, and if you need to dig deeper, you can. So we'll skip the math for now. But this is a method that tries to estimate where points move from one frame to the next. So if we look at the method in OpenCV, it's calc optical flow pyramid LK. The pyramid is actually, it's pretty cool. What this is doing, it's making a pyramid of images where it's starting with a full res image and then it's taking a down sample and a down sample and a down sample and making smaller and smaller images. It's a cool technique. We don't quite have time to talk about it in this class, but it lets you solve problems at multiple scales. Into this method, we pass our 2 images, gray 1, gray 2. We pass in the corners that we found from the first image when we did that corner analysis. And we get out the next set of points is the main thing we get out. So we get a next set of points. So I'd like to visualize those together. So let's have a look here. Yeah, here we go. So here's one way to visualize them. So in magenta, I've plotted all the points in the first image, and I've plotted the same points in the blue image, the points that have been tracked, basically. And I've plotted how they line up. So look carefully with me, right? And you'll see that for the most part, they're pretty good. We'll look at this in a different way, but I think some of these are wrong, but mostly they're really not too bad. So these have been matched up pretty well. Let me show it to you in a different way that I think will be a little bit easier to see what's going on. And this is really, we start to get into what's known as optical flow, which is, it's what we're doing, but it starts to look like flow. So what I've done here is I've taken the, I think I've taken the after image, so one of the 2 images, and I've drawn a line between the 2 points that were detected. So each of these lines represents the beginning, the point that was detected on the first image, and the point that was detected on the second image. And by looking at all of these lines together, you can actually see how the camera's moving, which is kind of cool, right? And in this case, the subject is fixed and the camera is moving, right? But it could be the other way around. But it gives you a feel for the flow, for the motion of the object. And here you can see that the camera is clearly just doing kind of a nice pan around the object. And you can see that some of these points are a little bit off, like this is off, right? But for the most part, you see a nice flow field. And this is a very common technique. And I think we've looked at this video before, but here's a little video from Tesla. And we talked about this a little bit in that video, and I do not really want the sound to be on. But in this video, and I think this is cropped for some reason, interesting. So way off to the side here, how can I, if I do this, maybe, give me 1 second. Yeah, there we go, cool, okay. Really what I wanna do is, that'll be full screen on my monitor though. All right, bear with the small size. So if you look in this Tesla video, you see all these green streaks that are kind of down here on the trees and stuff. So what Tesla is doing in their driving stack is they are doing optical flow, probably not Lucas Canade optical flow, but it could be something similar. They are tracking the motion of these objects on the sides of the car, basically, doing this optical. So you see all these green lines that are flying by. It's the same exact green lines you see here, same idea. But maybe a good question is why, right? So why would Tesla care about the motion of these objects in the scene? So one reason is they may track the motion of cars, for example, but that might be a little bit of a different pipeline. One thing you can do is if you can find the motion of static objects around you, then you can estimate how the car is moving, which could be valuable in a number of different ways. And there's probably other stuff they're doing with it, but in their video here, they've shown their optical flow calculations or their results of their optical flow algorithm on the environment, which is pretty cool. So optical flow calculations like this are useful in all kinds of robotic applications, including autonomous cars. We're talking mostly about 3D reconstruction, but robotics and robotic navigation has a lot of similar problems to what you bump into in 3D reconstruction. Okay, so that's optical flow. And now what I really want to get into is when might it fail, right? And I'll just kind of put my screen here so I won't give away any kind of answers. Cool. So this, you've seen optical flow, and I didn't really spend any time talking about how this method works. Let me just spend 1 little minute talking about Lucas Canade optical flow. So with optical flow, what you're really doing, and none of these pictures quite show it quite like I want. Let me just give you, I'll go here and I'll kind of give you the idea. So we have a starting point, and with Lucas Canade optical flow, you are searching the neighborhood. So you're saying, okay, here's my starting point, here's my new image, let's start at my old starting point, let's search the neighborhood, the local neighborhood, and let's see if I can find a match. That's the idea, right? So throw it in the chat window, when could that be a problem? When could searching the little neighborhood that you started in, when might that break down? Any ideas? When could just searching the little neighborhood that you started in your next image, if you have a series of images, yeah, so larger motions basically, right? So in a lot of problems, you're not going to have those kind of dense images. You might have 2 images from a very different viewpoint. And if you do, then optical flow is really going to struggle. So I'll show you what I mean here. So here's 2 viewpoints that are further apart, right? And let's see how we do, right? So here's optical flow for oops, that's the same image. I think I didn't run this line first. If I do this now, we'll really, yeah, look at that. So there's optical flow for 2 images that are really far apart. And it's because it's impossible to really start searching the neighborhood when the images get too different. So optical flow is really good when you have a tight series of images, but when they get too different, it can really struggle. Here's a nice little animation. And what I've done is this is taken from a larger video. And if I take the video frame by frame, 1 frame at a time, and I do optical flow from each frame to the next frame, I get very nice tight little lines like up in this left corner, right? Now, if I move that step size to 2, right, and I say let's drop every other frame and let's just do steps of 2, then I get pretty good flow, but I see some gaps, right? Here and there it has some errors, but pretty good. This is a step size of 3, so dropping 2 frames at a time. This is a step size of 5. And then finally, if I try to go 10 frames, it really gets noisy. This gets pretty gross. So optical flow, using Lucas Canade's method, is good for situations like this and not great for situations like this. So, and as you can imagine, you're not always going to have this nice tight video, right? So there are cases where you're going to want other methods, and that's really where SIFT comes in. So SIFT is probably one of the most popular computer vision algorithms ever. And it can address these issues. So it's a different approach to this problem, and it can address some of the problems we see with optical flow. So Lucas Canade searches for the neighborhood of our old interest points, and SIFT doesn't do that. So SIFT takes a different approach. So let's talk about SIFT a little bit with our last few minutes. And again, part of the challenge, that we saw is if our angle is too different, the appearance of our interest points change, and they become very hard to track. So SIFT was written by this researcher named David Lowe, a very prolific researcher. He was at the University of British Columbia when he wrote this. I think he's at Google now. For some reason, I looked for a few different pictures of him online, and this is I don't know, this picture is very creepy. It was the least creepy picture I could find, but for some reason this picture really creeps me out. I don't know why, but I'm sure he's a nice guy. Just this picture, really, I don't know what it is, but it just gives me the creeps. But really great research that he's done here, and I'm sure he's great in person. But I don't know if you think it's creepy or not, but it weirds me out. All right, so he published this algorithm called SIFT. It was patented for a while, which we'll talk about in a minute. And SIFT takes a different approach here, and if you read the paper, there's a lot of math. So it's like a 30-page paper, very mathematically heavy. It's brilliant, lots of really cool ideas. And he uses a bunch of unique ideas. One of them is called scale space. I'll just cover that idea of scale space briefly. The idea is we do this thing called a difference of Gaussians, or a DOG. If I taught this class 5 years ago, I would have spent a lot of time on this, but with deep learning, we kind of shift our focus a little bit, but it's still a very relevant technique. So a difference of Gaussians, the idea is we take our image and we make a bunch of copies of it, and progressively we make the image blurrier and blurrier and blurrier and blurrier. So we make more and more blurred images. And then we take the difference of each pair. So we do the sharpest image minus the first blurry one and make this difference, and we keep going kind of up this pyramid. When we get to a certain blur, we downsize the image and we do it again. And instead of solving or looking for feature points in the original image, we look for feature points in this three-dimensional space that we've made of difference of Gaussians. So it's a really cool idea, very creative. And it does a lot better. So solving it in this space instead of in just a two-dimensional image space gives you better solutions. And it's because it makes your algorithm a lot more scale invariant. So if you have a feature that's kind of bigger, that's like 10 pixels wide, it's way easier to catch it in a downsampled image than it would be in the original image. So the SIFT, so the SI stands for scale invariant. And this is one of the reasons that it's scale invariant, is because they solve the problem in scale space where you're in this 3D space that's made up of different resolutions of your image. It's a really cool idea. Okay, so that's part of SIFT. Another reason that SIFT is very robust, and it's a robust way to find matches between images, is because of the way they do key point descriptors. So what David Lowe did in his paper is he takes a region of an image, imagine this is a 16 by 16 grid, and he computes the gradient for all these pixels. So the gradient, it's like an edge detector. You can remember we learned the Sobel edge detector, for example, back in module 1. And you take all these gradient directions, the direction of the edge or the pixels for each point, and instead of just directly, using this as a kind of a feature to compare against other pixels or other interest points, he does what's called a histogram, right? So a histogram of gradients technique. So here he's kind of binning. So like if you have a gradient pointing upward and another gradient pointing upward, these two get added together, and you compute a gradient in all 8 directions, basically. So you make this histogram where you say, okay, most of these points are pointing in that direction, but some are pointing in this direction. So you do this binning thing, basically. And by doing this, it makes the feature descriptor more invariant. And wow, talking about that, I burned through 345, so I'll go ahead and wrap up here. I don't have a good cliffhanger to leave you on, except that I think the patent for SIFT expired last year. So before that, you couldn't use it without paying some royalty fees, but now I think you can, I think. But we'll finish next time talking about feature descriptors. And then as far as the rest of this module, we'll spend some more time talking about calibration and transformations and how to really get into this 3D stuff. So we're making good progress. We actually only have, wow, only two more lectures. Okay, cool. Yeah, so we have 2 more lectures on this next week, and then next Tuesday we have a guest lecture. Now is really time to be working hard on your projects. That's coming up soon. And then Arvind and Rohan, let's make sure we discuss the groups for the Module 6 Programming Challenge. We'll probably do the same groups as your project groups, but we'll let you know about that. We'll make an announcement before the end of the week. So great, thanks for your time today, guys. We will see you, today's Thursday, so we'll see you on Tuesday the 8th. Have a nice weekend, and do be working on your projects.